Okay, hello people. In this video I'm not going to be programming, but I decided to talk about some specific algorithm that I have been working for the past couple of days. And yeah, maybe it will be interesting for someone because I think it looks cool and the algorithm itself is pretty complex. I will try to go through the code and I will focus not on the algorithm itself because I will provide you a link where you can read about it on your own and it would be better than me explaining it. But I would rather focus on the part that implements visualization, right? Because I want to take an algorithm and make it visual. So yeah, let's just jump straight into code. But I don't know. Okay, maybe actually it's better to go through the book itself. So I was using this book. It's called Harker's Delight. It's really powerful. It contains like a lot of bit manipulations and like architecture sets, and it contains some cool algorithms like how to turn off bits, turn on bits, and things like that. Yeah, and there are much more. I'm just because I only started reading that, and it explains about floating points and many other things as well, and does everything in C. So there is what I was interested in is this Hilbert Curve algorithm. Is basically you have a square, unit square, and curve fills in the space like of the square, and it can be implemented either in 2D or in 3D space. I haven't got into 3D space because I don't know how to implement that. I only finished with 2D. Maybe it's better actually to show you how the program works. So yeah, if I run the program, you see like Hilbert curves of different orders trying to fill in the space. And yeah, in the green square you can see Hilbert curve of I don't remember, of the fifth order, this one, and this is like the Hilbert curve of the fourth order, third order, second order, and the first order respectively. So yeah, nothing special. It just goes in some kind of a fashion and tries to fill in the space of the square. Would be nice actually to make it work in 3D, but it's gonna be more involved. So yes, okay, and let me go back to the book itself. So what we have here is some explanation of how the algorithm works, and it is a recursive algorithm, but I mean the implementation is recursive, but I'm pretty sure that you can rewrite it with a for while loop or make it even stack based. Yes, okay. So on the pictures, the picture figure 16.1 shows you like the Hilbert curve of the first order, starting from left to right, the second, and the third order as well. And here are some more iterations of this algorithm, because so this one gigantic is like probably sixth order, but I'm not sure. You can play around with the code that I will put the link into the description, and try to make like a Hilbert curve of arbitrary order. I hope that will be helpful. So here is like an explanation of all the steps, how the algorithm works, and and here is implementation in C. That's like the direction where the line segment should go, and the rotation. You have to read about it on your own because it's pretty involved. and I spent like maybe 3-4 days of the preparation trying to understand the algorithm itself, and then 2 days on an actual implementation in C++. And here what we have is, let me take a look. Yes, the complete C program which computes the Hilbert curve of of arbitrary order, and you pass the order as a command line argument. And what it does is actually prints you the lengths of the line segment on each stage and the coordinates x and y of the line segment. Because if you take a look at this in one of those pictures, you can think of it that this segment has length 1, right? And it starts from 0, 0, it ends at 0, 1, and then this segment, I don't know whether you can see clearly or not, let me increase a bit, zoom in a bit. And this segment has the length or the distance along the curve 2, and it ends at 1, 1. So here should be like the point 1, 1. And this segment has distance 3 along the Hilbert curve and has coordinates 1, 0. And you can apply the same rule for the curve of arbitrary iteration. This doesn't really matter. What else I want to say? And yes, okay, so here is the author talks a bit about how to compute the coordinates based on the distance, and he talks about states of the algorithm itself. So if we enter, for example, state A, we can transition what kind of state we can transition. And there might be if I'm not mistaken, from state A we can transition to B, A, and D as well. So yeah, you have to look it up for yourself. And this is like a transition table. What else? There are some more advanced techniques of computing distances. I'm not sure. I looked at it briefly, and I was more focusing on, okay, I understand algorithm, how do I visualize it? But yeah, there are some more things if you're interested in, which are pretty involved and require a depth, deep knowledge of bit manipulation. And there are some algorithms how to compute the coordinates based on the segment distance, etc. And even logical circuits are included in order to compute the coordinates. So pretty cool algorithm, definitely check it out. I can show you again, and we will go through the code. So yeah, I'm using for each curve, I'm creating a separate thread, and that's why it looks like a simulation. We'll get to it in a second. So yeah, okay. So the main, and I was using the Windows 32 API because that's the easiest way for me to render. I probably could have rendered that into the bitmap into the bitmap and saved into the file, but that's how it is currently. So creating a window, nothing special, registering a class, setting the window size. What else? Checking whether we can sleep, creating context, resizing the deep section, and that actually would be our buffer that we will be rendering our curve into, and here we will be displaying the buffer, off-screen buffer, to the screen. Here I set up some variables like offset x, offset y, segment width, and segment height, and this is actually the function which renders all the curves. And you might ask a question why it's outside the for loop or the while loop or the game loop, whatever you can call it. And the reason for that is because I create like threads and I detach them. And this is done in order to be able, in order to actually display each iteration of the Hilbert curve. So whenever we rendered a single segment, we display it on the screen. If we rendered one more segment, line segment, we display it on the screen. And that's why you are able to see like this kind of animation. But we'll get to that function. Offset X and offset Y are the basically how many pixels we have to get from the lower left corner to the place where we start rendering the Hilbert curve, right? So that's pretty straightforward, and that is the like, okay, that's not the widths, but probably I should have named it differently, but I can show you what it corresponds to. So that's basically the parameters of a single like line segment. If you take a look at this segment, the widths, yeah, it's not a good name. It probably should be opposite. Like the width should be 4 and the height should be 20, but it depends what kind of segment you're looking into. For example, if you consider this segment instead of this, that's correct. It has the width like 20 and the height 4. But they're the same all the time. Yes, okay. And let me go to the Hilbert curves function, and probably it's better to start with a header file. So the program contains of 2 files, which is a header file, this one, and the CPP file. The CPP file contains the Windows code as well as the logic for Hilbert curve as well. So if you take a look at the Hilbert.h, we have some vectors here, and that's like helper vectors in order to so this one is used for the color, and this one I don't even remember whether it's used somewhere, probably like to retrieve the dimension of the window or something. So we have an off-screen buffer, that's our buffer that we are rendering our Hilbert curve into. That's like the state, whether we are running or not, whether the window is running, the program is running, sorry. Then we have a device context. Those things are not necessary. I just made wrappers around them. So whatever I created in device context, I don't have to release it manually. So that's why I wrapped it into the class. And device context is needed in order to display our off-screen buffer into the window. There is like a structure sleep information, but that's again, it's not like part of the algorithm itself, rather the Windows Windows 32 implementation, right? Because I have to check whether I can sleep or not. And that's again, that's a wrapper, so I don't call time end period manually. And that's, I think, the most important. Obviously, you can do like clean up and rearrange the things, but I was more focused on the algorithm itself. So here, everything is simple. We have a step function. You can find it in the algorithm, and you can in the book. And we have the Hilbert function, which is the recursive function that actually pretty much does everything. So yeah, this one, right? Okay, and inside the step function, so it's basically step function computes the x and y position of the line segment where we are in the Hilbert curve. And inside the step function, I actually issue a draw calls in order to be able to draw line segments. So I specify the direction, the color, and the buffer to draw to. And in order to create like a Hilbert curve instance, I specify an offset. We already talked about it. That's the offset from the left lower corner, and this offset X and offset Y, and they determine where we start rendering our Hilbert curve, right? And we have like a segment width, segment height, we've talked about as well. Then I implemented like this operator, call operator, in order to be able for this thread to call an instance like of this class. And I'm passing the buffer, the direction, the rotation, and order. And that's the most important of the Hilbert curve. And you can see the match with the, if I go to the algorithm itself, you can see the direct match with the code, since we pass in the direction, the rotation, and order here as well. And we call in the Hilbert in order to start rendering the curve. I have some private members. This basically segment X and segment Y correspond to the coordinates of the line segment along the curve. So they are modified as we render the curve. And they have initial values 0, 0. So now we can go to the CPP, and I think maybe I can start from the top. I have some include files here, some types, nothing special, then including Hilbert.h file, some global variables, rand range. I use it for generating random colors. So just generates a random integer number from in range. Well, the function itself generates an arbitrary range, but I'm using this function only to generate random numbers in range starting from 0 to 255, right? And what else we have here is round rail 32 to int 32. And that's like the rounding function, and I'm pretty sure that I'm using it for the color as well, right here. Then we have the function draw rectangle, which draws any type of rectangle to the off-screen buffer, and you probably not have to, but you could rewrite it with vectors and pass like the min point, the max point, and render the rectangle between them. But I'm just specifying everything manually, so it's rectangle min x, rectangle min y, and min x and min y is the lower left corner, and max x and max y is the upper left corner. And then the color of the rectangle that we are going to render, and the frame width, and I will go into talk about it in a second, what it means and what it can be used for. So what we do next is then we clip our rectangle, because, for example, if the user specified that the starting point of the rectangle is less than 0, which is obviously we won't be able to render it on the screen. So we just clip the region and say that the starting point, if it's negative, then it's better to equal to 0. The same applies for the like maximum, if the point, any point, either it's a minimum point or maximum point, right? The lower left corner or the upper right corner. If it's greater or equal than buffer width, then we just clip it to the buffer width. So no matter what we pass to this function, it always succeeds and never fails, right? Because we always clip by the region of our buffer. So we do it for all the points that we pass here. Then we compute the color. That's just regular normalization, not normalization, but we unpack the color, because I can show you later, maybe I can show you even now, the color itself. So I won't be able to pass the color like this, but I have to convert it to values between 0 and 255, so then I can pack it inside unsigned 32-bit integer and put it into the pixel. Write it down, right? So I'm doing this here. I'm using and left shift as well. So that's going to be the value of B value, G value, and R value. I'm not worried about here. I'm not like concerned here about the alpha value since I'm not using that. So yeah. And we have gotten to the point where I have to explain about the frame width, and this basically what happens. No, not what happens, but this is basically an ability for us to draw like the frame rectangle, only the frame of the rectangle, and without filling it in. And this variable corresponds to the width of the border of the frame, right? Here we have to make sure that actually the width or width multiplied by 2, because we'll draw the same frame width on both sides, right? For both sides of the rectangle, we have to make sure that it's less than or equal than rect max minus rect mean, which is basically the width of the rectangle, and this is the height of the rectangle, right? And this is where we write all the information into the buffer. We iterate over like height, and then we iterate over all the pixels in width, and we just write the color, so nothing special. And here is like the step function, and that's actually the most important, but no, not actually the most important. The second level of importance after render Hilbert curves, because this is where the trick happens, how to display it as a simulation, and how to basically render multiple Hilbert curves at a time on different threads, but we'll get to it later a bit. I'm using some C++, but that's not much. So yeah, what I was thinking about is that, okay, we have this step function. Again, you have to go through the algorithm on your own and draw it on paper, because I'm not going to be able to explain to you without drawing on the screen how the algorithm works. But what I can say is that we received a direction, and we ended with 3 basically to determine which kind of direction we have to draw a segment, either to the right, up, to the left, or down. So 0 corresponds to the right, that we have to draw the segment to the right. And that's actually what I'm doing. I'm just drawing rectangle to the right and slipping 20 milliseconds, and then advancing the x, because x coordinate, because we moved like one step to the right, we have to advance the x and y, the x coordinate of the Hilbert curve itself, right? So if the result of direction and 3 equals 1, then we have to go up, and that's actually what I'm doing. I compute mean x, mean y, max x, max y for the rectangle, and I draw a rectangle up, slip 20 milliseconds as well, and then I increment the y. The same applies to the left. If you decide to go to the left, that's basically a bit tricky for the left and down, because you have to compute max x and max y first, and then mean y and mean x and mean y second. But the idea is the same. We draw the rectangle to the left, and then we slip 20 seconds. Oh, I'm sorry, 20 milliseconds. segment X, and yeah, we have to decrement like a segment X. Down, okay, and that's the same idea for when we have to draw a segment which goes down. So we compute like the lower left corner of the rectangle, upper right corner of the rectangle. We draw the rectangle and then we slip 20 milliseconds. So the slip function is crucial here because it allows us basically to see the animation, because if you think about it, the drawing is executed on a separate thread, but we display in the buffer every frame. So that's why we are able actually to draw one segment and display it on the screen, then draw the next segment and display it on the screen, and so on and so forth. So that's how it works, and this is like the Hilbert function that you saw in the book itself. There is nothing special. I'm just following the algorithm, but what I do is I randomly generate a color for the segment, and that's why when I run the application, you can see like this. Every single segment in the line has randomly generated color, and that's why it looks like it is. So yeah, before doing a step, before actually making a draw call, before drawing a segment, I'm generating a color and I'm passing the color to the step function. Yeah, and finally, like the core function of this whole program is render Hilbert curves, which takes the buffer that we are going to render into, and the offset X, offset Y we've talked about many times, segment width, segment height as well. There are some variables which are common for Hilbert curves of all the orders. It doesn't really matter whether it's like Hilbert curve of the first or second, third or fourth order. They use the same variables. So that's like the initial direction, the initial rotation, and rotation corresponds basically the I think it would be better if I bring it up. So you can see that author explains, okay, the transformation of the order 1 Hilbert curve, and the order 1 Hilbert curve is this. U curve with a net direction to the right and a clockwise rotation. So the U net direction to the right, it looks like this, and then clockwise rotation, if I'm not mistaken, it goes like this. So like it looks down, right? And here is the algorithm which explains, okay, so what do we need to do in order to come from the Hilbert curve of the order 1 to the Hilbert curve of the order 2, and that's where rotation comes in. So we're changing the rotation and the direction as well. So yeah, these things are just draw calls in order to draw a frame. So it just looks better. So for example, you can see the green frame here, and yeah. For this, I decided not to draw frames because they are, well, it's not needed, but maybe you can rewrite the program whatever you wish. Then I set the order of the Hilbert curve, create an instance, and I create a thread, and then I pass like an instance and the parameters. So this is going to be the buffer, direction, rotation, and the order, and then I detach the thread. So then it starts the execution, we start rendering into the buffer, right? And that's fine because we're rendering in multiple locations, in different locations, right? Because here we're creating like, I don't know how many, 1, 2, 3, 4, 5 threads, and all of them are read access, so that's completely fine, right? Because no, wait a second. Yeah, it doesn't really matter whether it's read access or write access. Currently we're writing into the buffer, but we write in different locations, and we are not reading the data at all. So it doesn't make sense to make it thread safe, or to wrap like the buffer into the mutex, some custom data structure which has a mutex and which checks whether some kind of thread is trying to write into the buffer, then lock the access for all the other threads that are trying to write to the buffer at the same time. I don't want to do that because that's not necessary. As I said before, I'm rendering in different locations, different curves of various orders. So yes, the same happens for, and then I advance like an offset in order to be able to draw the next curve. Because if you take a look at the application itself, so here is the first offset, this point, and the second point is going to be this offset. So I have to advance it so that they don't overlap with each other, because you will see a mess on the screen. I draw a frame as well, and then I set up the curve of the fourth order, create an instance, again exactly the same code, creating a thread, detach the thread, then I offset the y, and the reason why I offset the I, so the x is already offsetted, so I go to this point, to this point, and start rendering Hilbert curve of the third order here. Okay, what else do we have? What else do we have? Okay, so yeah, and the same, like for any amount of Hilbert curves, you can like continue as this list, but if you have to figure out, okay, maybe you have to increase the window size in order to fit more curves, or you can play around with like the width and the height of the line segment to make it smaller, so we can fit more curves into on the single screen. So whatever you want, right? And yeah, there are some functions, but they are not related to the algorithm itself. They are Windows 32 specific, like the main procedure, and that's the function which takes in the off-screen buffer and displays it into the screen, and that's the function which allocates memory for the off-screen buffer. So yeah, and that's how it works actually. I don't think that I have anything else. I can show you again. Yeah, I don't know. I just was curious about like Hilbert curve. I knew about it, but I have never like I tried to implement it once on my own when I was younger, but it was really hard and I struggled a lot. I didn't know about threads and how to animate this curve, and I couldn't figure out the algorithm itself because it is complex in fact. So yeah, as usual, I will put a link in the description so you can play around with the program on your own, and maybe I will put some additional information about the algorithm and the book that I was referring to. So yeah, I think I will be finishing for today. Hope it was helpful, and at least you learn something. Maybe not how to implement the algorithm itself, but that, okay, such a thing exists, like the space filling curve, which is called Hilbert's curve, and that's how it looks, and that's how you can write the program in order to implement that. Okay, thank you for watching.